And if there are any questions about these things, please feel free to ask. And today in the afternoon, there is an exercise session, so we will discuss the solution of these problems that I've given you yesterday. And tomorrow, there will be hopefully time to discuss the solutions to some problems that I'll give you today. So yesterday, we started by discussing the O2 model. In the O2 model, we discussed mostly the broken phase, in which there is a Goldstone particle that's called the superfluid phase. And we discussed two aspects of that phase. One aspect was the existence of these vortices. And we argued that these vortices are in fact not real particles because their energy diverges like the logarithm of the size of the box. So they can never be created in an infinite volume limit. They are not actual particles. And then we discussed what happens to the system when we perturb by a magnetic field in some pi-lengths, or we just break the O2 symmetry by a cosine potential. And if we do that, we argue that these vortices, the core of the vortex is then connected to a long string-like object or a flux tube-like object. And in this case, the energy would, of course, diverge linearly as the size of the box. So the divergence gets even worse. So here, the divergence with the size of the box would go like linearly, and here it would go logarithmically. So you were supposed to try to understand this configuration for your homework problem. And then to contrast these facts, we discussed just free Maxwell theory in 2+1 dimensions, free U1 gauge theory. We discussed the existence of monopole operators, which are these abstract operators that lead to the breakdown of the magnetic U1 symmetry. And we discussed the fact that the photon in 2+1 dimensions is nothing more than just an Ambu-Goldstone particle for the magnetic U1 symmetry. Then we discussed the fact that if you put a point charge in 2+1 dimensions, there is a logarithmic divergence at long distances from the energy density in the electric field, very much akin to this fact about vortices. And then I mentioned that when we add monopole operators to the Lagrangian, if you just take the Lagrangian of pure Maxwell, you add a monopole operator into the action, which is hard to write explicitly, but you can do computations by expanding in this perturbation. So if we do that, I've argued, well, I mentioned that the electric charges are then confined. And instead of the electric field spreading radially, like you're used to seeing from classes in electromagnetism, the electric lines are now confined into a flux tube. And this is Polyakov's confinement mechanism. So that's sometimes called in the literature compact U1. So this is how particles are confined in U1 gauge theory in 2+1 dimensions. Once you add monopole operators, they're confined. Now, people who simulate this model on the lattice cannot prevent these monopoles from being added to the action. And that's why people say that U1 on the lattice always confines, because it's just hard to prevent these operators from being generated on the lattice. OK, so we see that point-like charges are very analogous to vortex cores. Basically, that's the map. So point charges and vortex cores are very similar. And it's a true fact at the level of first quantization. So you can think about these point charges as being very heavy probe particles that we can add to this model. Or you can think about these vortex cores as being very heavy particles that exist in this superfluid phase. And at that level, at the level of first quantization, it's really true that these two theories are very, very similar. However, the statement of duality is much more profound. It's not at the level of first quantization. The statement of duality that I'm going to make is about when these particles, the vortices and these particles, become dynamical. So second quantization. You can create them from the vacuum and they fluctuate. It's not just at the level of the formal properties of these particles as probe particles, heavy probe particles. So let us make a statement. Let us therefore get a little bit closer to defining what we mean by duality. So the phases of this model with epsilon equals 0, we discussed a lot. The phases of this model with epsilon equals 0 were a trivial gapped phase. and then a superfluid phase where the U1, where there is a Nambu-Goldstone particle. So the SO2 is broken spontaneously to nothing. And then there is a phase transition point described by the O2 Wilson-Fisher fixed point, or the XY model. So here we have the XY model. The fixed point, well, there is a conformal field theory. Let's just write conformal field theory. Okay. Now let's try to understand the phases of the gauge theory. But we need to make these particles dynamical. We want to have actual propagating charge 1 particles in the theory, because here the vortices are finite energy. Here the vortex core is just a point where the symmetry is restored. Let me explain why for a second. Remember that we parameterize the field in this fashion. So a vortex core is a point around which phi 1 winds. So for this to be consistent as a field configuration, you have to send the absolute value to 0 deep at the core of the vortex. That costs some energy, but that point is within our field configuration, and it costs some finite energy. So here, to really compare these theories, we need to go beyond this approximation where these are heavy probe particles. So we need to add some dynamical charge 1 particles to this theory too. So let's now discuss the theory of just a U1 gauge field coupled to a scalar field of charge 1. So here I'm going to introduce some notation that I'll use throughout. So this is not the same scalar field. The scalar field here was called phi, and the scalar field here is going to be called phi hat. And the mass squared here is not the same as the mass squared here. Here it's m squared, here it's going to be m squared hat. Then we have phi hat squared, and then we have phi hat to the power 4 with some lambda hat. So let's discuss this model now. So we already know a lot about this theory. In particular, in the unhiggsed phase, we just discussed many of its properties here. So are there any questions about that before I begin analyzing that model? Any questions that are left over from yesterday or what I said now? Yes? Yeah. It's in the strict infinite volume limit, this is problematic. But if you have a finite big tank, then it's okay. It would be you could create vortices, and they see that in the lab. In infinite volume, you always need to have a vortex and anti-vortex. It's also not a big deal. They can be widely separated, and it would cost some logarithmic energy. In infinite volume, this is a finite energy excitation. Sorry. In finite volume, this is a finite energy excitation. In infinite volume, strictly speaking, it's an infinite energy excitation. But it's not a big deal. You can put an anti-vortex very far away. So there will, and they see that all the time in the lab. They see vortex, anti-vortex excitations in superfluids. They're heavier than ordinary excitations, but they still exist. And they can be induced by putting various chemical potentials, like chemical potentials for the SO2 symmetry, for instance. Yes?
I didn't really get to define the monopole operators. You know, you're going to go back to that later?
I was not planning to, so I can do it now. The monopole operators are, have you ever seen, I mean, it would be somewhat easier to explain if do you know two-dimensional conformal field theories? Not so much. Some. So you see in quantum field theory, the local operators that you encounter in ordinary, like in the course work on quantum field theory, are just operators that are made out of local fields, products of local fields, and then you need to do some kind of subtractions to make sure that there are no self-divergences. So people do some kind of normal ordering or something of that sort. Now, people have realized some decades ago that there are also good local operators that cannot be expressed in a local fashion in terms of the fields. So you have to define them in a different way. So they can be defined by their abstract properties, like their operator product expansion or how they talk to other fields. Or they can be defined by path integral methods. So the definition that I gave was with path integral methods, where the monopole operator at point x is defined to be such that when you compute its correlation functions, the corresponding path integral, the gauge field that appears in the path integral has to have a monopole flux. So you take a point x, and if there is a monopole operator at this point, then you remove this point, and instead you have a sphere. Okay, you just remove a tiny, tiny epsilon size sphere, ball. You remove an epsilon size ball from space, and then your space looks like R3 minus a small ball. And you define the path integral such that the flux of the gauge field on this S2 is 1. So you just integrate the field strengths over this S2 and you get 1. So it's like a Dirac monopole configuration. And so you're allowed to do the path integral with this boundary condition. And now to show that this is a good local operator, you have to establish lots of properties. You have to show that it has good correlation functions. If you put two such operators, then you get some correlation function. You have to show that it has good correlation function, that it has good operator product expansion, and this has been done sort of by experience, that people have done lots of computations and it works. And there are analogous constructions in two-dimensional conformal filters. If you ever look at the C=1 models, they have what's called the twist operators or winding operators. Maybe in string theory you have seen winding operators. They're defined in a very similar fashion by removing a two-dimensional ball rather than a three-dimensional ball. Okay? So in principle, you can do calculations with this procedure. You take a small ball, and then you take epsilon to 0, and you get good correlation functions. Any other questions? Yes? That's a, well, in the O2 model, there are just configurations of the field which can be described classically by having some winding for a little phi and having absolute value phi going to 0 at the core of the vortex. So there are some kind of classical solutions, approximate classical solutions. And you can construct them by taking a vortex, an anti-vortex, and just construct an approximate classical solution that almost minimizes the energy. It would not truly minimize the energy because they always want to attract, but it kind of almost minimizes the energy. There is just a logarithmic energy. So it's an approximate, having a couple of vortices is an approximate classical solution. Now in supersymmetric gauge theories, and also in some model that I'll mention soon, there is a situation where these vortices are actually, the energy between two vortices exactly cancels out. And so you can construct actual solutions of the field equations, actual classical solutions of the field equations that describe multiple vortices. Okay? Any other questions? Yes?
Can you also explain the necessity of the Euclidean spacetime?
This picture is best understood actually in Minkowski spacetime. It's just a particle that's moving. It's a vortex, right? I'm interchangeably using Euclidean and Minkowski. When I write Lagrangians, I typically write them in Euclidean space, not to get confused. But a lot of the physics that we're talking about is best understood as real-time, in Hilbert space interpretation. For example, this whole discussion makes much more sense in Minkowski space, where we have vortex particles and they're moving and so on. Okay? Yes? Yeah. That's what I'm going to tell you now about. We're going to talk about the other description. This is more like a superfluid, and on the other side of the duality, there will be something that's more like a superconductor. And this will be like the abricos of tubes. This will be magnetic monopoles. This will be abricos of, in the other side of the duality, this will be more like the abricos of tubes that you know. You'll see in a second. Yeah?
You have finite volume. Is the monopole charge conserved or something? Do you have to create both a monopole and anti-monopole?
Yeah, so this theory, just pure Maxwell, even if I add additional fields actually, this is a very general fact in 2+1 dimensions. So gauge theory coupled to any number of fields always has a conserved symmetry. ordinary conserved current, which is like this. This is always conserved. And the interpretation of this conserved quantum number is that the total magnetic flux at any instant of time is the same. So once you create some magnetic flux, it cannot disappear. M1 is a local operator. Yes, M1 is a local operator that carries charge under the magnetic symmetry. Okay, and therefore, if you act with M1 on the vacuum, we create a configuration with a magnetic charge, and that configuration with magnetic charge is the magnetic vortex that I'll discuss now. Any other? Okay. Well, let me just say something before I move on. Strictly speaking, well, this is correct. This is independent of the vacuum of the theory. But as I said, the magnetic symmetry is spontaneously broken in the Coulomb phase. There is an expectation value for M. So this will just create a photon, which is the Goldstone boson. So this will just create a photon, okay? Which is the Goldstone boson for the magnetic symmetry, since M1 is charged under the spontaneously broken symmetry. But in the Higgs phase, which we'll discuss now, this will create a magnetic vortex. In both cases, these quantum numbers are conserved, except that here they are spontaneously broken. So when you have a spontaneously broken symmetry, the conservation laws are a little bit more subtle. You have to add a pion, and, Okay, so let's discuss this model in a little bit more detail, and hopefully that will also clarify the questions here. So we already know a lot about this model, especially in the limit of large positive m hat squared. Because that's the limit that we discussed here when there is a Coulomb field which is unhiggsed. Okay, here there is an unhiggsed Coulomb field, so we already know a lot about the large m hat squared limit, and we can also address Nathan's question here more precisely. So when we have this charged particle phi hat, which is extremely heavy, it's like going back to first quantization. It's not going to be created from the vacuum. It's non-relativistic, and it acts like a probe particle. So inserting it in if you just take a very heavy charged particle, you put it in some point in space, it will create this radially outgoing electric field, and the energy will be logarithmic. But the theory is gapless in this limit, because there is a free photon. There is a massless photon. So here there is a massless photon. Okay. That's fact number one about this phase. Fact number two is that the magnetic symmetry is spontaneously broken. And the massless photon has been already previously identified as the Nambu-Goldstone particle for that symmetry. So since that symmetry is spontaneously broken, its conservation is not as nice as it may. So that's Nathan's question, as it may be in the other phase. And another fact about this limit, well, I'll just state these two facts. Okay, now let's analyze the limit of large negative m hat squared. That's another interesting large negative m squared. I sometimes write it like this, large m hat squared. Well, in the literature, people, you would use this notation. When people say m hat squared much, much smaller than 0, they mean sometimes large negative m hat squared. It's not a very good notation, but I'll just use it sometimes. So in this limit, the physics is actually easier to analyze, but a little bit more rich in terms of the excitations. So in this limit, you all know from class that there is what's called the Higgs mechanism. Okay, this is the limit where there is a Higgs mechanism, and as you know, the photon, the one polarization of the photon, just eats the radial mode of the phase mode of phi hat. And the radial mode of phi hat is massive anyway. So clearly in that limit, the theory is gapped. So clearly it's gapped. And because it's gapped, the magnetic symmetry cannot be spontaneously broken, for otherwise there would be a massless particle. So U1 magnetic is unbroken. And here we can address the question of what are then the particles that carry U1 magnetic symmetry, because it's unbroken, and therefore the word identities are a little bit more intuitive. So does anybody have a guess of what are the particles that carry magnetic charge in the Higgs phase? You probably know the answer. Somebody already said it like a few minutes ago. So these are the Abrikosov strings. Let me explain, why this works. So consider phi hat, which is phi hat times the phase. Okay. So since phi hat, the absolute value of phi hat is non-zero, the gauge symmetry is Higgs. Now, we can again consider configurations around which phi hat winds. But there is a crucial difference between these configurations now and the vortices in the O2 model, in the broken phase of the O2 model. The difference being that here this was a massless limit. That was the case where the Goldstone bosons were actually massless. But here there are no Goldstone bosons. The phi hat is eaten by the gauge field. So it turns out that in this case, these vortices actually have finite energy. So the reason that they have finite energy, so there are magnetic vortices here. U1 M is unbroken, and we have magnetic vortices. Okay, the magnetic vortices carry U1 magnetic charge. Now I'll explain why they exist. So the reason that these magnetic vortices now do exist and have finite energy rather than logarithmically divergent energy is the following. So the Lagrangian previously was d phi squared. And we did this kind of estimate that if the Lagrangian is d phi squared, when you have a winding mode at long distances, you have a logarithm. However, now the Lagrangian is not d phi squared. There is a gauge field. So the Lagrangian is d minus b. D minus b times phi hat. This is just the covariant derivative squared plus other things. Okay? So now, when you get rid of the radial mode, you have like a Stuckelberg-like action, right? We have a Stuckelberg-like action. So in the infrared, we get something like d phi hat plus b, or minus b in my conventions squared. So now a winding mode for phi, a vortex-like configuration for phi, does not necessarily have infinite energy because we can tune or we can choose the gauge field configuration to be such that the logarithmic divergence cancels out. So by picking b to be like 1 over the distance with appropriate indices, we can cancel the divergence. And so what you have to remember from this discussion is that in the Higgs phase of the U1 gauge theory, the magnetic vortex has finite energy rather than infinite energy. Okay? So the magnetic vortices carry U1 magnetic charge and they have finite energy now. Okay, so this is the physics of these two limits. We can add a little bit more details here. So here SO2 was broken to nothing. We had vortices that had infinite energy. But here in the trivial gapped phase, we have the phi particle. The phi particle now carries well-defined SO2 quantum numbers because SO2 is unbroken in this limit. So you see that the physics of these two models is extremely similar, except that the diagrams are flipped. So if you just take this diagram, flip it, it's extremely analogous to that. Like all the properties match. It's gapped. Here there is a phi particle. Here there is a magnetic vortex. Here U1M is unbroken. Here SO2 is unbroken. And on the other side, SO2 is broken. And here U1 magnetic is broken. So it's exactly the same phase diagram, only switched. So therefore, people were compelled to conjecture that the conformal field theory here is exactly the same as there. So both models, in fact, describe the exact same phase transition, described by the O2 fixed point, the O2 CFT. And here you also have the O2 CFT. So the two models are exactly the same. That's the idea. They flow to exactly the same phase transition. And there is a complicated map. The physics is very different, but it's just a question of language somehow. So there is a duality. Yes?
So do you know where is it is larger than 0
No, this is, okay. This is a great question. You might be, let me just, I'll answer that in a second. There is something confusing about this duality, which is the following thing. So the duality says that, in fact, these two seemingly different models are exactly the same. So we can write it in the following way. So one model is 1 over 2g squared f mu squared plus d b phi hat squared plus m hat squared phi hat squared plus lambda hat phi hat to the 4. That's one model. This model is supposed to be dual. That's the notation for being dual to just d phi squared with a half plus m squared phi squared plus lambda phi to the 4. Okay. This is duality. This is called particle-vortex duality. Why is it called particle-vortex duality? I hope by now it's completely clear. Because the phi particles in the unbroken phase here correspond to the finite energy vortices in the Higgs phase here. They're both finite energy. And in addition, the vortices here in the broken phase, which have logarithmically divergent energy, correspond to the electric charge excitations in the Coulomb phase. So there is this is why it's called the particle-vortex duality. But there is something weird about this duality because the number of parameters does not match. And that I'm getting to your question. Here you see that there is g squared, m hat squared, and lambda hat. And here there is just lambda and m squared. So here there are 2 parameters, while here there are 3 parameters. So you can ask, how is that even conceivable? That these two Lagrangians would yield the same physics if they have a different number of parameters. Hmm? Oh, yeah, you could say that even the number of degrees of freedom doesn't match. So this looks insane. So many things work out, but the number of parameters doesn't match. And as the gentleman here observed, what's your name? Philippe. As Philippe observed, the number of degrees of freedom doesn't match. So this whole thing looks insane. But you agree that there is there are also some virtues. It's not just like that doesn't make sense, right? So let's address these 2 points. Actually, they're addressed in the same way. The point is that these 2 theories have various scales, mass scales. And you can ask, what about these theories have various mass scales determined by g squared, m squared, and lambda. And the physics of these models, in general, if you try to simulate them on the lattice, would be a very complicated function of these various scales. And it would be very different at various energy scales. The resolution to these 2 paradoxes is that we're not claiming that these 2 Lagrangians describe the exact same physics at all energies and for all values of these parameters. The duality is an infrared duality. Okay? So the notion here is that in particle physics or high energy physics, infrared duality is a key concept. So unlike the duality in n equals 4 supersymmetric Yang-Mills, which is a conformal field theory, and therefore it's an all-energy duality, this is not a conformal field theory. These are complicated models with complicated different Hamiltonians, and they're not the same. But if you look at long-distance physics, they are the same. Now, you could say that the long-distance physics is stupid. It's trivial. And indeed, if you look at this phase diagram, here the long-distance physics is just a compact scalar. Here the long-distance physics is empty. There is nothing. So there is only one point where the long-distance physics is interesting. That's the second-order phase transition point, where there is a conformal field theory, an interactive conformal field theory. And indeed, the duality does not say that these phases are exactly the same for all values and you get the exactly same particles. The duality only says that in a small neighborhood of this point and at very low energies, the 2 theories agree. But it's a finite neighborhood. It's not an infinite neighborhood. It's a finite, small, open neighborhood where the physics agrees, and you have to go to very low energies. So we go to low energies, and we focus near the phase transition. Focus near the second order phase transition. So the statement is not that the mass of the phi particle here in the unbroken phase exactly coincides with the mass of the magnetic vortex in the Higgs phase as a function of some parameters, because that couldn't make any sense. But at very low energies, near the phase transition, it does make sense. So the duality is only a statement about close to the phase transition, but you're allowed to explore the two phases. You're still allowed to explore the two phases, but you're not allowed to go very far. In fact, if you go, well, in more complicated situations, there could be several phase transitions. The duality could be different for each. There could be a different duality for each. So this addresses both paradoxes, because the number of degrees of freedom is something that we count high energies. If you do high energy experiments in this theories, they are as different as any two theories could be. They have different number of degrees of freedom, different spins, different excitations with different spins. So there's nothing to discuss. Okay? And also the number of parameters is not a contradiction, because some parameters become irrelevant at long distances. Yeah. No. So the duality states that they flow to exactly the same fixed point. So sometimes people would draw the following diagram to emphasize this. So there is some kind of parameter space. For one theory, this could be m squared. For the other theory, it could be m head squared or minus m head squared. And people would draw this kind of diagram. One is the gauge theory plus scalar. So this is U1 plus phi hat. And here you just write phi. This is an extremely shorthand notation. Okay? This is the phi particle theory, and this is the U1 plus phi hat particle theory. They flow to the exact same O2 Wilson-Fisher fixed point. But their deformations are different. So we can write a map. So near this fixed point, the fixed point has certain primary operators or certain interesting local operators. So now we can write a map between, we already understood a lot of the ingredients of the maps between these two theories, but we can be a little bit more explicit, and we can write a dictionary. So phi squared is a good local operator in this theory. You can ask, what does it map to in this theory? At least this should be true around the fixed point. Well, the main point is that it maps to minus phi squared. Why is there a minus sign? Does anybody see in this map? Yeah, because of the inversion, right? Because when you had to invert the phase diagram. So you could say, what does it even mean? These are positive definite operators. But no, as you know in quantum field theory, when you multiply two local operators, you have to renormalize them. And so this is not a positive definite operator. So this map does not contradict anything. In fact, there could be a 2 here, but this 2 is kind of insignificant. You could renormalize what you mean by phi and get rid of the 2. So only the sign is important. So that's why people just write minus, and that's it. So this is one element in the map. Another element is that there is the magnetic symmetry on this side of the duality. Sorry, what am I doing? Mu rho, F mu rho. So there is this magnetic symmetry. And this obviously maps to the U1 symmetry of the SO2 model, which is just phi star d phi. This is another element in the duality. Okay, what about phi? Can somebody tell you? What does the phi? Phi is a good local operator because there is no gauge symmetry of this side of the duality. There is no gauge symmetry on this side. Okay? So phi is a good gauge invariant local operator. What does it map to? It's a question to the audience. We already said that in the diagram. Exactly. Very good. So phi is the monopole operator of the gauge theory. You can be more ambitious and ask, what is phi hat? This is not an extremely good question because phi hat is not gauge invariant. We're not supposed to map it. But if you want to be bold and try to say something nevertheless, you would say that this is this bed vortex. This is the bed vortex, the one that has logarithmic energy. However, people won't usually write that because this whole thing is questionable because it's not gauge invariant. It's not gauge invariant on this side, and it has logarithmically divergent energy on this side. So both concepts don't really exist. They are approximate concepts. So people would typically omit that from the map because it's not rigorous, but it's qualitatively true. So, well, this is more or less the map, and there are more elements in this map that we discussed. And so that's what I wanted to say about, I wanted to say what is the status of this theory. Of course, you cannot prove it. Nobody can prove that this theory for some range of parameters flows to this fixed point, and we cannot prove it analytically. So while what I told you about the probe particles and the probe vortex particles is rigorous, this is a conjecture. You can think about it as a conjecture, but people have essentially proven it on the lattice by simulating these two models. So you can say that this is proven on the lattice. But from the theory point of view, it's more like a conjecture. This is one rare instance where some duality is actually considered to be proven. Like nobody seriously doubts that this is true for some range of energies and for sufficiently cleverly chosen couplings. And okay, so this is a rare instance where we actually know that this is true. It's a non-supersymmetric infrared duality. Yeah. Well, to prove theoretically, you mean one big challenge is to show that the transitions are second order. There is no way to do that, even for this model. If you could prove that the transitions here and here are second order, and if you could prove that these are in the universality class of what's called the XY model, then you would be done. But this seems to me to be like light years away from what we can presently do. We cannot do such things, like not even close. So we have to put the models on the lattice and measure the correlation lengths. And if the correlation length goes to infinity, or at least gets very large on the lattice, then we are somewhat sure that it's in the right universality class by measuring subcritical exponents. Then we can declare victory. But nobody can directly do any computation in the continuum to show that. Yeah. That's an excellent question. Indeed, there is a supersymmetric version of this duality. Are you interested in me telling you what it is, or you can do it maybe in the exercise session? Yeah? There is both an n equals 1 extension and an n equals 2 extension. And in fact, mirror symmetry can be viewed as a certain extension of that. So this is a non-supersymmetric version of more familiar to some supersymmetric dualities. Okay? Okay, let's move. Any other questions before I move on?
Maybe I missed the first line. First line is just saying phi squared is related to phi squared?
Minus. There is a crucial minus sign here.
So I should be able to try that from the third line?
Oh, no, you cannot take the square root of the first line.
No, I want to take the square of the third line.
Yeah, so that would mean, that's a good question. So Nathan is asking whether we can derive this from the first line. So you could multiply this by phi star. And then this will have to be multiplied by m1 star. And you'll have to take the operator product expansion. And in the operator product expansion of a monopole and an anti-monopole, there are neutral operators. And the operator that appears is essentially phi hat squared. Yeah. So when we write this map, what we mean is that in the conformal field theory, there is a well-defined set of primary operators, abstract primary operators. So one abstract primary operator is SO2 invariant, or O2 invariant. So on this side of the duality, phi squared goes to it, and the other side minus phi hat squared. And this is another primary operator, which is in the doublet representation of SO2. So, okay. Any other questions? Yes.
In the first model, what is the mass dimension of the gauge coupling?
What is the mass dimension of the gauge coupling? G squared is 1. Yes, that's why U1 gauge theories in 2 + 1 dimensions are notoriously hard, because the gauge coupling has positive mass dimensions, and so they become strongly coupled. In fact, we've already seen that by adding a monopole operator, we could lead to confinement. So you want gauge theory can even confine in 2+1 dimensions because the gauge coupling has positive mass dimensions. I perhaps should say something else, another thing about this model, which is a little bit more advanced. But if you ever read the condensed matter literature, it's extremely useful to know. So actually, in this model, it's known from lattice simulations that it does not always have a second-order transition. It's only for some choices of lambda hat and m squared and g squared that it does flow to a second-order fixed point. And then it's known numerically that the second-order fixed point is in this universality class, and then we have duality. So qualitatively, there are two regimes. One is when the gauge coupling, the scale that is set by the gauge coupling is very low compared to the scale that is set by lambda hat. And the other limit is the opposite. So there are two limits. One is when lambda hat is much bigger than g squared. And the other is when lambda hat is much smaller than g squared. Okay? Now, in this limit, it's known that it's second order. And you cannot establish it analytically, but with some additional assumptions, you can do analytic computations. So this is a second order. And this is where the duality actually holds. You have to take lambda hat to be big enough. How big? I mean, you don't have to. There is some kind of critical GC squared. So the ratio between lambda and g squared could be like 2, and above 2, you're already second order. It doesn't have to be parametrically big. So, but for big enough lambda hat, it's definitely second order, and there the duality definitely holds. But in this regime, it's first order actually, because of the Coleman-Weinberg effect that you might read about if you are interested. And here, the duality is kind of void of content because there is no interesting long-distance physics. If the phase transition is first order, remember that then we have this picture, right? And there is no conformal filter. There is no non-trivial long-distance physics. So the duality is almost void of content. So what we really mean when we discuss this duality is that lambda hat is sufficiently big. We cannot compute analytically how big it gotta be, but we know that when it's sufficiently big, it's definitely true. Now, in the condensed matter literature, these two limits are called type 1 and type 2 superconductors. And there is a qualitative difference between these two limits. In one of them, these magnetic vortices attract, and in the other, these magnetic vortices repel. And when lambda is exactly at the critical value between these two phases, then the magnetic vortices are free to roam around, and you get a moduli space of magnetic vortices, at least classically. Okay? So this is just a slightly more advanced comment. Okay, so now I want to switch to more recent developments involving the Chern-Simons theory. So recently, people have constructed vast generalizations of this duality by including the physics of Chern-Simons theory. So I want to now start teaching you what is Chern-Simons theory, and then eventually I'll present some generalizations which involve Chern-Simons terms, non-trivial generalizations.
Is there any duality in the V equals 4?
Well, that's a big open question, whether there are interesting. We don't know of interesting non-supersymmetric dualities in D equals 4, unfortunately. Well, U1 gauge theories are boring in D equals 4. At long distance, they are always free. So there are no interesting dualities. You have to probably talk about non-abelian gauge theory. And well, I can tell you some examples. There were some discussions recently in the literature, but I won't say that they are as on solid footing as this one. They are not confirmed, they are speculative, there are still discussions about whether they might even be right or not. So in 4 dimensions, it's not as developed as 3D. And it's in fact one of the most interesting problems in this field, to try to look for non-supersymmetric dualities in 4 dimensions. Okay, so now we completely changed subject, and I want to dedicate maybe an hour, maybe more, to Chern-Simons theory. So I have like 10 minutes. I'll just start now, and then we'll continue. No. Oh, yeah, I'm sorry. I have 45 minutes, so yeah. Yes? Yeah, you had a question?
Yeah, one unrelated lecture, but can we please turn the air conditioning again? Okay, let's take a
both because I've hit both sides. So who wants the air conditioning on?
I don't
Doesn't want it on.
I don't see a second side.
It can be on, but not so cold, and you're happy.
So there's actually a temperature gradient. So it's usually warmer up in the top. So if you're cold, turn it off if you want.
Okay, I'm switching gears to the next topic, which is Chern-Simons theory. And we'll start from a billion Chern-Simons theory. So we'll start from U1 Chern-Simons theory at level K, where K is an integer. I'll tell you in a second. I'll tell you soon why it has to be an integer. So then we have epsilon mu nu rho mu.
Sorry, medium version of 2+1. Right?
Yeah, I mean, as before, when I write Lagrangians or write equations of motion, it will always be in Euclidean space so that I don't get confused. But when I discuss the physics, it will often be in a Hilbert space interpretation.
This is 2+1.
Yeah, this is always going to be 2+1. This whole set of lectures is, well, almost exclusively about 2+1. Yeah. So there, let me just, I'm sorry, I want to use lowercase notation for gauge fields as I've been doing before. So I'm using lowercase notation for gauge fields which are dynamical. Okay, dynamical gauge fields like A will be lowercase. So A mu is a U1 gauge field. So this is a special kind of quadratic free theory that you can write only in 2+1 dimensions because we're using the epsilon tensor, and it's a gauge invariant under the U1 gauge transformations. Indeed, if we do a U1 gauge transformation, d mu lambda, then this becomes d of lambda a d mu a rho mu, and then there is an epsilon mu nu rho. So if you do a gauge transformation, this whole thing is a total derivative, obviously. And so the Lagrangian is not invariant, but the action is invariant. So this leads to a gauge invariant action. So the action is gauge invariant. So that's an interesting alternative to gauge theory, to F squared, that exists in 2+1 dimensions. So let's first discuss the physical meaning of this kind of gauge theory. And to understand its physical content, it's best to try to couple it to sources, classical sources like charge density or current density, just to try to understand the response of this theory to electric charges. We already understand a lot about what happens to when you put an electric charge in ordinary Maxwell theory. You just get the Coulomb force, which you learn about in school. But here, there will be completely different physics, and you might not have seen it before. So that's what I want to show you. So we will couple this theory to some classical current. So A is the fluctuating field. We pass integrate over it. But J mu is a given function of space-time. It's a given current for some particles which are very heavy. Because I'm using Euclidean signature. In Minkowski, if I was to write this Lagrangian in Minkowski signature, there would be no I. Okay, so J mu of x is a given function of space-time, which consists of the charge density and the current density for some particles. Okay? It's a given function. You can choose this function to be whatever you want. Now, you all know the Maxwell equations, which describe the electric and magnetic field that is associated to some current or some charge density. So the analog equations here are the Euler-Lagrange equations for this action, where you take functional derivatives with respect to A, and they're trivial to derive. You get k over 4 pi times epsilon mu nu rho, f nu rho. That's equal to j mu. That's the covariant relativistic version of Maxwell's equations in Chern-Simons theory. Or we can invert this equation to write an expression for the magnetic field or the electric field, both of them, I mean, which is 2 pi over k. And then there's epsilon mu nu rho, and then j rho. Now, it's further useful to observe that these equations only make sense if the current is conserved, if it satisfies the continuity equation. So you remember from school that the current must satisfy this. This is just the continuity equation. It's just saying that if charge moves, then it creates some current for charge. So this equation is tantamount to the Bianchi identity. So this whole system of equations is inconsistent unless the current is conserved. So this is the Bianchi. This gets retranslated to the Bianchi identity. And in fact, you could see it already here in the Lagrangian. This would not be gauge invariant unless the current satisfied the continuity equation, the conservation equation, okay? So let's just write these equations in components to get a little bit more intuition. So the charge density is k over 2 pi times the magnetic field. I'm just writing this equation in components. Or and ji is k over 2 pi times epsilon ij eij, where E is the electric field and B is the magnetic field. So what is the most obvious difference between this and Maxwell equations? Does anybody see? Somebody who doesn't know the answer, maybe from before. Yes? First of all, yeah, in Maxwell's, in the system of Maxwell equations, if you put charges, you don't create magnetic fields, you create electric fields. So that's one glaring difference. But there is a more pronounced difference here, a more deep difference somehow. Yes? Exactly, so they're non-dynamical. What does it mean, dynamical? Yes, so in Maxwell's equations, if you specify the charge density and the current density, it does not uniquely determine the electric and magnetic fields. Why? Because there are waves, and you can always add a wave at the speed of light. These are dynamical equations. That's what you might have meant, right? But here, once you specify the charge and the current density, the magnetic and electric fields are completely fixed. That means that there are no waves, so no propagating photons. So this theory doesn't have propagating photons, but it doesn't mean that it's trivial. It still creates interesting electromagnetic configurations when you have sources, but by itself, it has no propagating degrees of freedom. There are no particles in this theory. So there are no waves. No particles or no waves. For this reason, this theory is called the topological field theory, because it doesn't have propagating degrees of freedom. It only leads to some interesting global effects, which we will see soon. So this is why this is called the topological field theory. Okay? Well, that's one reason it's called the topological field theory. There is a more precise reason why it is like that. So, so now let's do some, to get more intuition, we'll just study now what happens when we put some charged particles. So in some sense, in the condensed matter literature, you would sometimes see the phrase that in Chern-Simons matter theory, so this is like a matter, non-dynamical matter, and this is the Chern-Simons part. You would sometimes see sometimes see people saying that the electric and magnetic fields are slaves of the particles. What does it mean for them to be slaves? It means that they don't have their own life. The electric and magnetic fields are completely determined by the matter particles. So they're slaves of the matter particles. So let's imagine some charge density, which I'll take. These are just external charges of infinite mass, and I'm allowed to put them wherever I want. Like I can just stick them to the floor. And I'll take them to be static in time, just not to complicate things. I'll just take them to be stationary. I won't let them move. We can then, as a homework exercise, generalize it. So I'll take charge 1 particles. So the electric charge is going to be 1. I'm not going to introduce a coefficient E because I don't need it. So the charge is just going to be 1. So it's going to be a sum over delta functions. So delta of x minus xa, where xa are the locations of the particles, and we'll have n of those. Okay, so I'm just describing n particles sitting in space and not moving. Okay, so using our formulas here, we can infer the magnetic field and the electric field. So surprisingly enough, the electric field completely vanishes. Even though these are charge 1 particles, the electric field just vanishes. So it's very different from Maxwell in all respects, right? The electric field just vanishes. But the magnetic field does not vanish. What is the expression for the magnetic field? The magnetic field is going to be 1 over 2 pi k sum, I'm just copying, of delta x minus xa. It's time independent. Oh, 2 pi is wrong. 2 pi over k. So the magnetic field doesn't propagate in space. It's localized to the particles. So each electric particle now carries magnetic field. And the magnitude of that magnetic field is, roughly speaking, 1 over k. That's what you got to remember. That now each particle is leads to a fractional magnetic field, which is 1 over k in some natural units. So each particle is therefore a little solenoid, right? So each particle becomes a little solenoid. Another terminology that you would see is that there is flux attachment. So you could say that the magnetic field is a slave of the particle. If the particle starts moving, the magnetic field will move with the particle. And then there will be also some electric fields that are generated. But basically, the magnetic field is attached to the particle. So people sometimes say the words flux attachment. So you attach magnetic flux to each particle. Yeah? Oh, no. I should have drawn one, but it's, yeah. Maybe, well, I don't know why. There is no reason I can think of. Yeah, okay. So you have probably seen the expression for the vector potential for such a configuration. Yeah.
Why are you calling these fields the electric and magnetic field, not the reverse?
What? Can you say again?
Because why you don't call the B field the electric field?
Oh, the question is why I'm not calling this E and this B? There are established conventions for what we mean by the electric field. The electric field is the F0, the time-space components of the field strength, and the magnetic field is the mix. But more seriously, the electric field is a vector in space. It has an index, EI. While the magnetic field is a pseudoscalar in space. It has no indices in 2 + 1 dimensions. In 3 + 1 dimensions, the electric field is a vector and the magnetic field is a vector. And they're almost interchangeable. There is a duality that interchanges them, but one is a vector and one is a pseudo-vector. In 2 + 1 dimensions, they're not even comparable because this is a vector and this is a scalar or a pseudo-scalar. Okay, so there is no sense of changing who you call what. Any other questions? Okay, so now you remember you must have seen in the past the Aronoff-Bohm phenomenon. Is there anybody here who does not know the Aronoff-Bohm effect? Okay. The whole point of the Aronoff-Bohm effect, if you remember, was that if you have a solenoid with a magnetic flux B, classically, the magnetic field has no consequences outside of the solenoid, but quantum mechanically it does have a consequence even outside of the solenoid because there is a non-trivial vector potential that lives outside of the solenoid, right? So similarly, we can write the vector potential that is associated to these solenoids. So the vector potential AI is, well, I'll just write AI. This is time independent because we don't have any electric fields, but it's nevertheless non-trivial. It's E, there is no E. It's 1 over K times a sum over DI. And what is the formula for the vector potential outside of a solenoid? It's a derivative of the phase, right? So it's DI, and then you have the argument of X minus XA. And you just sum over A. So these little magnetic solenoids do not talk to each other because it's a free theory. So the vector potential is just a superposition of the vector potentials of each magnetic solenoid because it's a free theory, and the equations are all linear. So this is the vector potential in space. Now let me define a homework exercise. A homework exercise is to generalize this to particles that are moving in space. Okay, so now we'll have electric fields, and your job is to find AIA. Your job is to find the generalized formula for AI and prove that it's correct. And please work in the gauge where A0 is 0. Okay? Is the homework exercise clear? So the physics of this model is really interesting because we have electric charges that do not actually lead to any electric field, but they acquire, like, each of them becomes like a little solenoid. So the interesting thing that is happening here is that when we move these particles, we get interesting phases, Aronoff-Bohm phases. And this is why people say that this theory describes anyons. So our electric charges, which started their life as ordinary particles, due to the Chern-Simons interaction, they become anyons. So our particles become anyons. And now we're going to compute the phases that the wave function picks when these particles go around each other. And we'll also compute the spin of these particles. So they started their life as ordinary spinless particles, but the fact that they because of this flux attachment, they become anyons, and furthermore, they acquire non-zero spin. So let's first compute the phases of when two such anyons are moved across each other. This phase is nothing but the Aronoff-Bohm phase. So it's an exponential of e to the IA. Why is there a coefficient 1 here? Because the particle that we're moving has charge 1. And this A is just this A. It's the same A as here. So that's really easy to compute. It's just an integral over the phase, the function which is like just the argument. So this gives e to the 2 pi I over k. So these are anyons, because when you move them across, you move them like this. These are not ordinary particles. They pick up a funny phase, e to the 2 pi I over k. Let me just generalize it. it will be useful to generalize it. A useful generalization of this formula is to ask what would have happened if we took a particle of electric charge Q surrounding a particle of electric charge Q prime. It's the same problem as before. You just put coefficients Q and Q prime in front of two delta functions. And then the magnetic field is going to be 2 pi Q or 2 pi Q prime. And the integral is the same. It's a trivial generalization. And the phase factor that you find in this case is 2 pi I Q prime over K. Q and Q prime have to be integers because they are electric charges of a U1 gauge theory, so they have to be integers. Okay? Now I want to tell you about the spin of the anion. This is a more complicated problem to compute the spin of the anion. So there is a conceptual problem that we have to discuss before we get to compute the spin, and which is, why is the spin even well defined? Why is the spin of an anion well defined? So observation number 1 is that suppose you have infinite space R2 and you put an anion. So that's an anion, okay? And you put this anion in the origin. So the Hilbert space of this theory in the presence of an anion still has a U1 symmetry, rotations around the anion. So the little group is still SO2. This is the little group. And therefore, it's perfectly well defined to ask, what is the SO2 quantum number of the ground state of that theory? Because the Hilbert space of such a theory would be in representations of SO2. So it makes sense to ask what is the quantum number of the ground state. Now, however, the spin is only defined modulo 1 because of the following reason. The theory doesn't meet local operators, such as F mu. Or, well, more precisely, let me just phrase it more physically. I want to phrase it a little bit more physically. So what I want to explain now is, why is the spin defined mod 1? So we can only discuss the spin of an anion mod 1. The reason is that physically, that you see, you might have thought that this theory is completely trivial in the infrared, because these particles are heavy, and the electric and magnetic fields do not spread anywhere in space. So you could ask, why am I even discussing this theory at long distances? The point is that this theory has non-trivial long-distance behavior, which is captured by these Aharonov-Bohm phases. So unlike ordinary quantum field theories, which you might have seen before, where the long-distance behavior is captured by correlation functions or by conformal field theory or by massless particles, here the long-distance physics has to do with Aharonov-Bohm phases between anions. So this is what we can observe in the lab. Even if we have very low energies, we can still do this experiment of taking two anions across each other very slowly, adiabatically, then we can measure the phase. Okay, so this is the low energy content of this theory. But these phases are independent of the fact that you could have, for example, taken your anion and put some particle on top of it. Take your favorite particle of spin 1 and just put it on top of the anion. Some particle that doesn't have any Aharonov-Bohm phases. So therefore, the spin of the anion is not really a well-defined thing within Chern-Simons theory. To really compute the spin of an anion, you need a full microscopic theory. Within Chern-Simons theory, the only thing that's observed, the only thing that you can measure is this Aharonov-Bohm phases and the spin mod 1. You cannot discern the spin of this particle beyond just putting an ordinary particle with integer spin. Is this more or less intuitively clear? Why it's mod 1, or should I try to explain it in another way? Huh? Try to explain it again? Okay, so you see, let's start from these Aharonov-Bohm phases. These Aharonov-Bohm phases are measurable at long distances if you do adiabatic experiments of taking the anions across each other. But of course, if the Aharonov-Bohm phases vanished, imagine that the Aharonov-Bohm phases were all e to the 2 pi I. what would have we said? We would have said that this is a trivial theory. There is nothing at long distances to measure. These are just heavy particles. They have no interesting long-distance dynamics, and there is nothing to measure, right? Now, the spin has a somewhat similar, the spin is more complicated. The spin is the eigenvalue of this little group when you put an anion, but it's similar in some way. So think about QCD, something like QCD, right? In QCD, there are no anyons. The protons and the neutrons and the mesons, if you just braid them across each other, they lead to trivial phases. So how could you stop me from just taking an anion and let's say I put some meson on top of the anion. I just take your anion and I put a small meson on top. I could make the spin change by 1 in this way. But I'm not going to be able, you're not going to be able to measure it. What you can measure is the intrinsic properties of these anions, which cannot be modified by sticking to them trivial particles. So in condensed matter theory, they would say that there are some trivial particles or transparent particles, and then there are the anyons. But the anyons are only defined modulo the transparent particles or the trivial particles. Okay? Is this a little bit more clear now? So when you compute the spin of the anyons, you cannot actually compute it as a number. You can only compute it mod 1. And this computation is a little bit harder, so I'll just tell you the answer. The spin of the anion with charge q is q squared over k. So it's a fractional spin. So it's q squared over 2k, q squared over 2k mod 1. That's the answer that you find. So the phase is easy to compute, but the spin is a little bit harder to compute. In fact, I can give you an intuitive explanation for the spin in a second. This explanation is a little bit ad hoc, but it works well in this model. So let's consider what happens when you take an anion of charge q and move it past an anion, well, across an anion of the same charge q. So from this computation of the phase, we see that the phase that we would pick up would be e to the 2 pi I q squared. So the phase that we would pick up here would be e to the 2 pi I q squared over k. Is this okay? Now, a way to define the spin in quantum mechanics is through the properties of the wave function when you exchange two particles. Correct? So if we exchange two particles, the wave function goes to an exponential of 2 pi I times the spin of the particles that we exchange. For example, from Fermi statistics, this works well, right? If you put spin equals a half, you get a minus sign. When you put spin equals integer, you get a plus sign, like for Bose and Fermi statistics. So with this definition of the spin, we can now say something, because this is like exchanging the particles twice. Like exchanging the particles is just a half of this. It's just like moving this particle here and then moving them like that. So you can interpret this factor as twice the spin. Okay? And therefore the spin is a half of this factor. And therefore the spin is q squared over k, over 2k. So that's an ad hoc explanation for why the spin is q squared over 2k. Okay, so we see the Chern-Simons theory does not have any interesting low energy degrees of freedom, but it leads to interesting topological phases. It leads to fractional spin and anyons. That's the conclusion from this discussion. Say again? Can these anyons are very massive. They're external particles. Oh, you're asking if we can make them low mass, if we can make them dynamical, or... So in this description here, the anyons were external particles, just charge 1 particles that I put in by hand, and then I just move them adiabatically. But in the next, of course, in the future, what we want to do is we want to make these anyons dynamical, so that they could be created from the vacuum, they could fluctuate, and then we will discuss generalizations of particle-vortex duality with anyons. But at the moment, these anyons are just external particles, like external charge particles. Okay? So the thing that I want to discuss now is the question of why is K quantized. I haven't yet explained why is K quantized. So I'll erase that. So all the formulas that I've written so far make sense even when K is not quantized to be an integer.
A force law, like the fluids doing the charge movement?
You're asking if the electric fields might cause the charges to move?
Yeah.
Well, the electric fields are, if you have an electric field, that means that there is a current, just because the electric field is equal to the current. Okay? But the electric field is only equal to the current as a delta function. So the electric field is just a sum of delta functions. In Chern-Simons theory, you cannot turn on an electric field throughout space because the electric field is a slave of the particles. There is no massless gauge field. The gauge field is massive, so you cannot turn on like a small electric field throughout space. That would cost infinite energy in Chern-Simons theory. You can only turn on electric fields that live on top of the particles, and they're just a sum of delta functions. It's very counterintuitive at first. You have to get used to this. Okay? Any other questions? Okay, yeah?
These are physical particles, and therefore these dimensional things. But how do you do this linear decomposition in the Hilbert space to find the...
You're asking how would you do it mathematically?
Yeah.
So mathematically, you would just take Chern-Simons theory, which was written here, and you would just take J mu to correspond to one particle that's sitting at the origin. And then it's time translationally invariant, because we just assume that this particle sits at the origin. So we have a well-defined quantum mechanical problem. You can put it in a big torus or in some space, and you can try to solve it. Or you can put it on a disk. So you just quantize this. You just go to the Hamiltonian, and you quantize this theory with this being just a delta function at the origin. And then you find a Hilbert space, a quantum mechanical Hilbert space. And in that Hilbert space, you can compute the spin by evaluating the SO2 quantum numbers of the ground state. So I can give you a reference to the original literature where this was done. So this formalism was so the Hamiltonian quantization was developed by, well, I remember some of the authors. Some of the authors are Schwimmer, Seiberg, Moore, and maybe Elitzur. I may have forgotten one co-author, but just look for a paper of these three people, and they do the Hamiltonian quantization in detail. The what? What is the reference? What does it mean to have a reference state? I don't know. No, the reference state is just a particle that sits at the origin. That's the reference state. Yeah, the little group is the stabilizer of the source. Now, the source is just a delta function at the origin. The stabilizer of that includes translations in time and rotations in space. So you can classify the Hilbert space according to energies and spin. SO2 cross translations in time. Yes, so you diagonalize the Hilbert space and you discuss the quantum numbers of the states under those quantum numbers, under those symmetries. Yes? The what? Yes, massive, yeah. Yes, this will be an exercise. I'll define it soon. I haven't discussed it yet. We'll discuss what happens when you add a kinetic term in addition to the Chern-Simons term. And then you can try to see that then there will be a massive degree of freedom, which is propagating, but it will be massive. So that will hopefully make everything more and more coherent. And it would explain why, when we drop the kinetic term, there is nothing left. except for these topological phases. Any other question? So now I want to describe, well, first of all, I should say that mathematically, well, there is a shortcut notation for Chern-Simons theory, which is A wedge dA. And you'll often see it written like that. It's just a shorthand notation for what we just said. I should just say that in general, mathematically, the path integral over gauge fields with this action, with an I, only makes sense when k is an integer. So k is an integer is just a mathematical fact. But physically, this can be understood as follows. So you can understand physically why it's better to have integer k in two ways. There are two, I'll give you 2 or 3 arguments that would hopefully convince you that you should better take k to be an integer. So argument number 1, this is not something that I'll prove, I'll just state. If you define the theory on a torus times time, if you put the theory, if you take the Euclidean space, the space-like section, to be a torus with periodic boundary conditions, then it's easy to show that you just quantize this Hamiltonian and you find that the number of ground states in this quantum mechanical model is k. So that should be an integer. That's a fact that I will not prove, but it's true. So that's one way to see that k must be an integer. Another way to see that k must be an integer, which is through these anyons, is that if k was, let's say, square root of 2, you will see that this is kind of horrible because essentially there will be an infinite number of anyons and an infinite number of spins. So if k is an integer, what you get is a finite number of anyons and a finite algebra of anyons. And this is much more physically desirable than to have, an infinite representation. So for integer k, what happens is that if you shift q, if you shift the electric charge by k, you get the same Aharonov-Bohm phases. So there is only a finite number of anyons and only a finite number of distinguishable spins. More precisely, if k is an even integer number, then you see that the spins and Aharonov-Bohm phases go back to themselves when q is equal to k. So the indistinguishable anyons for k even correspond to q equals 0 all the way to k minus 1. Because if k is even, k squared over 2k is an integer. So it's 0 mod 1. And likewise, the Aharonov-Bohm phases vanish when you put q equals k. If k is odd, then q goes to from 0 to 2k minus 1. And the anyon with q equals k is kind of special. It has trivial Aharonov-Bohm phases, but it has spin a half. So it's still an interesting anyon. And in particular, if you have some cycles on your manifold, you have to say what is the spin structure to define the theory. So for k odd, for this reason, this is called a spin topological field theory. And this is called a bosonic topological field theory. The difference is very subtle. It's whether or not there is a transparent anyon of spin a half. It will not be important for these lectures. I'm just saying it for the more advanced students.
Isn't it possible to have infinite number of anyons, and they are more and more massive, so that we don't?
Yeah, it's a great question. So there is a question which is being asked here, which is what's wrong with having infinitely many anyons with like arbitrary spins? So in principle, if you study the theory in infinite space on R2, I cannot personally see any problem. You could say that they're more and more massive, and okay, who cares? The problems, however, hit you in the face if you try to define the theory in compact space. So this model that you mentioned may seem okay on R2, but once you put it in compact space, it makes no sense.
Why?
For example,
Why? Why it makes no sense?
well, for instance, the number of ground states will be infinite. It will be an unphysical model somehow. Well, you expect the number of ground states on a compact space to be finite, or 1 in most cases. Having an infinite number of ground states or an infinite dimensional representation of the braid group is probably unphysical. It's a little bit reminiscent of Dirac's quantization condition. You could ask, why did Dirac insist it's kind of like Dirac's quantization condition. You could say, okay, why do we not allow for monopoles which are fractional? And the real answer is that you could, but then you'll get infinite dimensional representations. So if you want to have wave functions, wave functions in the presence of monopoles, which are infinite dimensional unitary representations, you need to have an integer monopole. If you try to quantize Dirac's monopole with fractional monopole charge, there won't be a strict contradiction. It's just that you'll find infinite dimensional representations. So it's kind of bad. Okay. So this is the physics of the Chern-Simons model. And what we will do in the next lecture after lunch is that we will try to make these anyons dynamical. That's where the exciting stuff is. As long as these anyons are pro-particles, I don't have much more to say. They're just anyons, and that's it. But if they start fluctuating and you get interesting, dynamical effects, then the story gets much more interesting. I also want to make one comment in relation to condensed matter physics. The special case of k equals 3 is very famous in condensed matter theory. It's a particular state of the quantum Hall effect, of the fractional quantum Hall effect. If you have ever seen this parameter in condensed matter physics, it's the case of 1/3, when the conductivity is 1/3. So this is a very special case. In this space, we see that there are 6 anyons. There are 6 anyons. And one of the anyons is special. It's the one where Q is equal to 3. That anyon has no braiding, and it has spin 1/2. So that anyon is basically just the low energy manifestation of the electron in the quantum Hall effect. So Q equals 3 is the electron. If you look at Laflin's wave function, that's exactly how it works. So in condensed matter physics, to construct the quantum Hall phenomenon, we have a magnetic field and electrons. But the electrons are not anyons. The electrons have just ordinary Fermi statistics. So you could ask, where do these anyons come from in condensed matter physics, in the quantum Hall effect? These anyons are emergent particles. Okay? They are just collective phenomena. But the electron still makes it somehow to the deep infrared. It's just this particular anyon. The other anyons have non-trivial braiding, and they cannot be understood by any weak coupling argument or weak coupling computation. But this can be understood. Okay. So there are some values here of k which correspond to interesting phases of the quantum Hall state and other systems in condensed matter physics. Okay. Yep. Well, I just said that there are special cases of k in which it describes the plateaus in the quantum Hall effect, fractional quantum Hall effect. So if the conductivity in the quantum Hall state is 1 over an integer, it would typically be described by U1 level k with some k Chern-Simons theory. This is the application of this business to condensed matter physics. Now, in the context of particle physics, Chern-Simons theory has a long history, and it has many applications, ranging from higher spin theories to various supersymmetry and many other things. Okay, thanks.